Thank you for joining this workshop. Over to you, John.
Okay. Good morning, everybody, and welcome in this fourth training workshop of a series that EU-IoT project is doing with the project, the most recently funded IoT projects of the European Commission. I am John Soldatos, Intrasoft International. So today, our session is devoted on IoT architectures, next generation IoT architectures. As I said, this is the fourth of a series of workshops. Maybe some of you have joined earlier training sessions. So we had last May first session on artificial intelligence and Internet of Things and edge machine learning. We had a second workshop in July that was for tactile internet and Internet of Things. And we had a training session during the IoT week this year, again on machine learning. So today we will be discussing different flavors of IoT architectures. I will briefly introducing the topic before giving the floor to our excellent speakers. And yes, we would like to see what are the structuring principles of leading edge IoT systems that go beyond the state of the art. And they include elements like 5G networks, tactile intelligence, blockchains, deep learning at the edge, federated learning, and of course, integration and alignment with different architectures like the Web of Things architecture. So that's what our today's workshop is about. And I think it's a workshop with an excellent content. We have from all the IoT projects, the recently funded, as I said, IoT projects, all of them are very good projects and very innovative. So we have actually top people from the coordination, right? So coordinators or technical coordinators or leading figures of these projects. And I'm talking about IoT Engine project, Ingenious, Terminet, Assist IoT, Intel IoT, and Vettel IoT project. So a lot of content, excellent content, rich content by some of the top experts in our community. And I would like to thank them in advance for being here and for their presentation. So going back to the topic of IoT architecture, if you just Google this topic, you're gonna find a ton of content. And actually, I've made a rough taxonomy again for the purposes of those workshops of all the IoT architectures in 3 strands. So we've got some architectures from standardization bodies. They are aiming at providing reference model at high abstraction level. And we have more specific implementation oriented architectures that usually, the big vendors like Amazon or Microsoft and others, Siemens are pushing. And of course, you will see a lot of application specific architectures. So the IoT topic is so broad, and you leverage Internet of Things technology and Internet of Things applications in different sectors, manufacturing, energy, smart cities, healthcare, smart home. So if you just, search for architectures in these verticals, you will find specialized IoT architectures. Why do we need so many architectures? I think the simple answer is that because the IoT, as we know, is not a single technology, right? But it's a pool of technologies and disciplines that you bring together to deliver pervasive applications that have to be sometimes human-centric and so on. So that's the reason, and you have different business requirements in terms of security, interoperability, actuation, integration with different objects and so on. So that's the simple answer. Why do we have so many IoT architectures and so much different sometimes architectures? So just to fix some ideas on the popular architecture. So we have architectures from standard bodies like Industrial Internet Consortium or OpenFOG. By the way, these two bodies are now merged together, so they are working together under the Industrial Internet of Things consortium. And what is interesting is that these are essentially, cloud edge architectures. If you just go and see the low-level implementation details, so they are pushing multi-tier cloud edge architectures for the implementation. Of course, there are more in our community. We have the Alliance for IoT Innovation, and there we have a specification of a high-level architecture that actually maps to different standards. Also, IoT has an IoT architecture models, and earlier in earlier years, EU projects played a role in specifying part of these architectures. Now, these are at high level of abstractions. These are general. These are meant to be models that enable you to derive different architectures. Then the same we have for standards like 1M, 2M, or ETSI, mobile edge computing. They are touching on different aspects, some more on the networking aspects and other in the analytic aspects. That going beyond this abstraction, if you just go to see Azure or Amazon AWS, you will find that there are reference architectures that are more simplified, more pragmatic, if you want, more implementation oriented. And this is what you actually do if you want to implement, you actually follow if you want to implement a pipeline in a cloud like Azure or like Amazon and so on. So I've just put a couple of examples here. And then we go to the application specific architectures. So we have specialized architectures for manufacturing, for smart grids, for smart cities. Sometimes these are also aligned to standards, reference models like the RAMI here from Platform Industry 4.0 in Germany, or NIST, a US concept for the smart grid. So having said all that, I'm gonna just, without further ado, give the floor to our excellent speakers to for a more in-depth discussion and for actually seeing more innovative concepts that arise from the different projects as we speak. I'll just take 1 minute to sell our training catalog. In addition to this series of seminars, we are creating, it's now on beta, but you can already play with it on the NG-IoT website. EU-IoT project has provided a catalog of training resources. So as you know, the seminars we are doing here, we don't explain the easy things. What is IoT, or how do I develop an IoT application with Python? But what we did instead is we created a catalog of different courses that you can search. And of course, you can propose even your own course and expand the catalog, but you will find a collection of over 100 courses from the major ecosystems like Coursera, Udemy, and so on and so forth. So having said this, I think, one thing is that we want you with us for the next workshop. So I think we will start from early 2022, January, starting with IoT-oriented workshops dedicated to 5G solutions, blockchain, and then other topics that they're not already planned, but are discussed, like IoT in data spaces, and maybe some thematic sessions. So I hope my introduction was not lengthy and was not boring, because I'd like to give the floor to our excellent speakers. As I said, some of the best experts we have in Europe on Internet of Things, and especially on the topic of IoT architectures. So I'll give the floor without further ado to Artemis from IoT Engine Project for the first presentation. And I will just invite you, to write your questions on the chat, or if you even, because we might have some buffer time in the end. So if you want to take the floor and ask something, just let us know in the chat, and we will allow you to unmute and ask your question and get the answer. So Artemis, the floor is yours. I hope everybody is going to enjoy today's workshop. Thank you very much.
Thank you, John, for the introduction. Let me share my screen. Hopefully you can see it, right?
Feel free to introduce yourself, right? This goes for you and every other speaker. Feel free to introduce yourself and your project in short before starting the presentation. Thank you.
Thank you, John. Thank you. So my name is Artemis Boulkidis. I am the technical director of Snellix Solutions. This is an SME in Greece, mostly focusing on IoT towards smart agriculture and cybersecurity solutions. And I also happen to be the IoT Engine technical coordinator. So today, before going on with the architecture considerations that we had in our project, let me briefly introduce the project, what we do, what is our focus, and what is our scope, of course. So if in one sentence I could say what the IoT Engine is about, it's about bringing IoT and in general modern technologies together, such as 5G, artificial intelligence, DLT, and all these beautiful technologies that also John mentioned before. So our cause is to bring them together in an optimal way so that we can deliver new tools and a community-based ecosystem that can enable, let's say, next generation IoT. And by this, we mean new services to existing platforms, new services in general, new platform opportunities, new collaboration paradigms, and of course, unlock any new business potential options that we have. So our core vision and principles, IoT Engine, as we say, is full stack IoT. So this means that we are dealing with all layers of IoT, starting from the component up to the communication, information, function, and business layers. We have multiple considerations in all 5 layers. And on top of those, we do have some quality attributes that should be respected at all times. And this revolve around interoperability, security, and privacy by design. Traceability, mostly using DLT, blockchains, and inter-DLT approaches, as well as data sovereignty by design. Having said that, our core technical focus, mostly related to this particular webinar today, we have defined the meta architecture. So we define this as an architectural design language for IoT platforms and services, which target mostly next generation IoT architectures, but legacy IoT architectures could be also supported, granted that some features get dropped. And we have a federation approach towards both the data and the services. So also taking the lead from what John said earlier about, for example, AI at the edge, we focus on privacy preserving federated machine learning for the training and distributed AI in general. As I said before, Intel DLT technologies to secure and enforce trusted data sharing. Regarding the models that we train, we use zero knowledge proofs to validate them. And we also have some meta level digital twin DLT enabled ones actually, which base their operations based on proper ontologies like SARE, for example. When it comes to communications, we support task offloading of microservices at a secure edge cloud location. We have support for 5G slicing, and we do have, let's say, interfaces with several relevant standards. Time-sensitive networking, and we have been researching on the definition and partial development of a 5G network exposure API. Last, we researched towards distributed IoT, cybersecurity, and trust. We have several approaches towards that direction, like supporting self-sovereign identities for trust management, machine learning-based cybersecurity auditing and active protection, for example, scanning the network for vulnerabilities or vulnerable devices and services. And we interconnect all this information using DLTs in a manner that everything can be verifiable via multiple DLTs, not only one. Regarding the validation of IoT engine, we do that in 7 countries with 7 living labs and lab tests, and we have defined more than 10 use cases. As you can see in this figure, we have a smart factory in Spain. We have twin smart cities in the north of Europe, in Helsinki and Tallinn. We support, we coordinate with Helsinki mostly in this directive. We have smart energy pilot and smart mobilities pilot in the general location of Umbria in Italy. And in Greece, in Peloponnese, we will have a living lab showcasing smart agriculture with autonomous vehicles and drones. On top of all those, to validate things related to 5G and functionalities that are not easy to deploy on the living labs, we also have 2 integration and network laboratory environments to test against. One is located in France, so it's one lab from Sorbonne University, and we have a combined trial laboratory in Aachen, Germany, from RWTH and Ericsson. Now, enough with the introduction. As I said before, IoT engine has defined, on top of an architecture, of course, a meta architecture. So the meta architecture takes on a higher level view, and it collects together architecturally significant choices, patterns, components, and viewpoints that exist in the literature and in the industry landscape. And essentially, it provides a foundation for the architecture and system design. So in our view, there are 4 main points of focus. The first one is the domain horizontal, which defines the domains related mostly to the use cases and the requirements of these architectures, of the meta architecture, sorry. We have a quality vertical. I'm going to also showcase that after. We have the architectural patterns vertical and the element view. So let's go and check what all these things mean in real life. So this is the meta architecture, and this is the quality vertical. So the quality vertical actually denotes several notions that should be followed on design level, so that we can guarantee that the operations and the services that are offered by the IoT architecture in hand is secure, interoperable, scalable. It features high availability and data integrity, data sovereignty, and it is performant regardless of scale. So it's this one is tightly related to scalability as well. But the important thing is to maintain a high quality of service and high quality of experience at the edge and at the cloud. The architectural patterns vertical, depicted in the figure right here, it features several architectural paradigms, such as, for example, the layered architecture, the microservices-oriented architectures, event-driven or Lambda architectures, together with core technologies and notions that could, and some of them should be used, so that we achieve the design of an architecture that is future-proof and can also incorporate legacy architectures. Examples of that is, for example, the 5G network exposure that I mentioned before, distributed ledger technologies, notions such as serverless computing and self-sovereign identities, research upon which we work in IoT Engine. And moving on, we have the elements view. So the elements view is more of a technological concept. It features several functional groups of multiple layers. So we have, for example, first and second layer of element groups. And essentially, this one defines technologies that they should be followed, so that all the quality views that we saw before may be in the end accomplished. So as a reference, we have the infrastructure, the federation, the workloads, element views. we have the things, the fog edge, automation, and analytics. And each one of those, they comprise several technologies and notions. As I said before, for example, the federation, there is a requirement to have a federation so that we can be scalable and performant in each given instance. Now, a few notes about intelligence in our meta architecture. As you can see in this, for example, figure, there are two vertical options for the elements view to support it. And these are the machine learning here at the end and the artificial intelligence. So they are defined like that because in IoT engine, they are ubiquitous. And we catalyze those via a machine learning as a service framework that we have been developing. The cause of this framework is to deliver automated machine learning pipelines and services, both to the project per se, but also to third parties. So in this context, we support an arbitrary number of supported technologies. Practically every machine learning related framework should be and could be supported. In the project, we do have explicit support for privacy preserving federated learning that I mentioned also before. We have active and continuous learning, deep learning, model training and polyglot sharing using frameworks such as ONNX, and generative adversarial networks in case one needs to generate datasets, or in our particular case, take some parts of these generative adversarial networks to offer cybersecurity services. I think that we had also provided a relevant presentation or another webinar towards that direction, so it would be good if you could also have a look at that. Having said that, the artificial intelligence part in IoT engine is catalyzed by Kubeflow. So Kubeflow is an open source framework exactly towards that direction, but we also offer explicit support for Git operations and greater integration also with meta-level digital twins. Now, we said about a high-level view of what the meta architecture is, what are the different points of view. We discussed about the machine learning and the importance that this one has. But the important thing when defining a meta architecture is to also identify which are the elements that should be considered so that another architecture is compliant with this, let's say, design language. So what we did in IoT engine is to take up all the four views that we have. So the quality vertical, the architectural patterns vertical, the element view, and the underlying ML/AI view, and try to identify a compliance baseline. So when it comes to the quality vertical, all the elements and requirements should be satisfied, because these ones, they mostly refer to essential things that every IoT platform should have in our view. For example, security or scalability. When it comes to the architectural patterns vertical, what we said is at least one should be adopted, with a small exception that we have forgotten something and we have not added there. But ideally we should, because there is also a continuous alignment task in the project, and this meta architecture is a living document, so it will be updated in the end. In any case, at least one of these well-known, let's say, practices and approaches should be adopted in order to guarantee, let's say, compliance to the meta architecture. When it comes to the element view, this one is a bit more peculiar because it's mostly technology focused. So what we said is that all security elements, they should be present. Baseline security indications that we have identified, for example, they are related to authentication and authorization, enforcement of SSL and TLS technologies, And basically, most of the elements that have been identified either way by ENISA as baseline security measures that every, let's say, IoT platform should comply to. Now, for the rest of the security elements, because the security functional group is just one of them, we have identified that at least one of its first level functional groups from its first level functional group, at least one element should be adopted. So in the case that we have a nested functional group, at least one of the elements of the nested functional group should again be adopted. And finally, when it comes to the underlying machine learning and AI framework, this one is desirable, it's not necessary. However, we firmly believe that the future of IoT is intelligent and most probably artificially one. Now, based on this meta-architecture specification that we identified as a project, we in the end derived our high-level architecture, and it is depicted in this figure. As you can see, this one is a layered architecture, and not only that, it's also based, extremely based, let's say, on microservices oriented architectures for each layer. And so this means that actually it comprises multiple and semi-autonomous layers, and each living lab that I mentioned before, they are able to feature their own instantiation. Some of these elements are missing, and in some others, for example, are missing. In any case, after a complete analysis of the requirements and what we would like to do, we identified that this particular architecture snapshot is compliant with the requirements of the meta architecture. So indeed, it could act as an instantiation, the first level, let's say, instantiation of the meta architecture that we have identified. And important thing here to notice is that this architecture is extendable, and it is open to other interfacing systems. And by systems, we mean devices and, of course, platform. As you can see, we do have support for modern, let's say, 5G-oriented communications. We also have device-to-device communications, for example, in order to increase 5G coverage in an area by multi-hop networks. We have support for the secure execution I mentioned before, and for the vulnerabilities detection. On top of those, we have the federated data sovereignty layer marked in orange, mostly based on DLTs and smart contracts. And on top of those, we do have the big data analytics and machine learning. And these are also based, they base their operation on top of this federated data sovereignty layer, particularly when it comes to zero knowledge proof for the models that get shared inside this federation that we have. And of course, in the end, we do have some support for actuation services and augmented reality. So last slide before I close the presentation, and I think I should be on time. This one has to do with alignment to standards. As you can understand, and due to the depth of the project task, and I guess this should happen also to the rest of the project, we're able to face it. Having said that, we have compiled an indicative list of the most important, let's say, relevant standards that we develop against and that we try to enrich. First of all, and most importantly, it's the 3GPP stack of standards regarding 5G networking. Then we adhere to the HCNSM AFTS 28.533 standard regarding slicing management. We do have contributions in IEEE 802.1. So regarding time-sensitive networking task group. And then we have the firewall protocol stack with the ETSI NGS-ILD protocol as most, let's say, representative. And then we do have several ad hoc standards that we are operating against, and we're compliant and interoperable. For example, like SAREF, GS1, and decentralized identifiers, so DIDs. This latter one is most related to the self-sovereign identities. So that was it. Thank you for your attention. I will be open for questions and discussion when the session ends. And hopefully it was not too fast. I try to condense things so that I'm on time. Thank you.
Okay, before moving to Ingenious and Karsten, I don't know if there are any questions in the chat. I think the question I would like to ask, because this is a complex thing, right? So I would like to ask the following. The first thing is, do an implementer has to take all of it, or you can just stick to parts of the architecture? And what's the word meta? By the way, this is a very popular word this day. I don't know if it was part of your project or it's a marketing trick that you just created for this workshop. The word meta is that it is just a blueprint for deriving more specific architectures, or that it is an architecture per se. So it's a meta. So I just use it as a blueprint to derive a more specific architecture. And do I need to take all, or I can get parts of it? That's one question. And another question is, how do you validate this? For example, with 5G, is it a lab or a field validation with 5G connectivity?
Excellent. Thank you for the question, John. First of all, no, it's not an architecture, it's a meta architecture. So it's, as you said before, a blueprint that one can use to derive architectures. So it's a collection of architectural patterns and approaches towards having future-proof architectural elements. Now, I had a slide regarding compliance. So ideally, in order to be compliant with this meta architecture concept and vision, when it comes to the various qualities, for example, the security, interoperability, scalability considerations, then it should be explicit that the IoT engine, the IoT developer or a platform provider is compliant to those, so that there are considerations towards security, interoperability, scalability, and high availability, for example. When it comes to the architectural patterns, at least one should be adopted. This one is so generic that most platforms should already be relevant to that, except for some monoliths, so very old ones. And when it comes to the elements view, so this one is the most peculiar. As I said before, we have said that we have identified that at least one element from all these boxes should be provided. However, again, we really believe that these are the absolutely essential ones. So practically every IoT platform should adhere to those. If something is missing, then for sure there is some functionality missing in this IoT platform, or is too narrow. Now, regarding the 5G validation, as I very briefly discussed, the full range of 5G validation will be performed in the Eurolab, combined Eurolab laboratory in Germany. So this one is a collaboration between RWTH in Aachen and Ericsson, Germany. And some of the trials, they will feature 5G, such as the Helsinki trial here in the smart city area. So regarding the 5G validation and the network part, it's a kind of a mixed bag.
Thank you, Artemis.
Yeah,
Unless there are any questions, I think we can move to Karsten, right, and Ingenious.
Yeah.
And I guess Artemis will
thank
be
you.
around for discussion. So Karsten, the floor is yours. Feel free to introduce yourself and
Thank you. So you should be able to see my slides now.
Yes.
Okay, perfect. All right. So yeah, my name is Karsten. I'm working at the Barkhausen Institute in Dresden, Germany, and this is an institute that is all about the trustworthy Internet of Things. And in this presentation, I'm talking about how we apply IoT ideas to the supply chain. So first about the project. So we are a fairly big consortium. So we have 21 partner organizations from 8 countries, from all these countries that you can see on the map. Quite a lot of us are actually in Spain, which is also where most of the test beds are located. So we have 2 ports in the project. One is the port of Valencia, another one is the one in Livorno in Italy. And then we have also a smart factory as a test bed and an actual ship provided by Costco. So yeah, but before I talk about the architecture, I think I have to talk about the use cases, because the use cases are kind of what are, yeah, they are setting the requirements that we have, and they define what we want to build and how we build it. And the first use case is, you could say, at the beginning of the supply chain, which is in automated factories. And it's about automating robots there. And in particular, the focus is on finding ways to orchestrate them from a centralized location, like an MEC that is very close by, that yeah, kind of can remote control multiple robots. That's the focus of this use case. The second use case is then about yeah, the actual goods and how to transport them. And we approach this from 2 angles. The first one is about the actual transportation equipment. And in this case, we have train axles on cargo carriages that we monitor using IoT sensors, and we perform some localized processing in order to monitor these train axles for defects. The goal of this is that we can get away from fixed maintenance interval, but do demand-driven maintenance, which allows you to reduce cost. And whenever there's a problem, we use whatever kind of connectivity is there in order to report to a control center that there might be a problem with one of the axles and the carriage needs to be removed or go to maintenance. And the other part about yeah, transportation is, of course, about the actual assets. So we deal with containers here and develop and deploy IoT sensors to monitor the conditions of the container, whether it's temperatures okay and so on. In order to make sure that the cargo is in good shape. Mostly this is about yeah, when it's on the seas and on a ship, but we also consider the in the use case the lag on land. And yeah, it's basically about enabling tracking or real-time tracking in locations where it's not previously possible using satellite connectivity, for example. At some point, of course, since we have 2 ports in the project, we are also trying to optimize ports. So here we focus on optimizing the time that trucks spend inside port and terminal facilities in order to make sure that there are fewer traffic jams and so on. And the approach is AI and machine learning based. So basically we collect data from everywhere on the port and also from external sources, like when are the ships arriving or where are they actually right now, and even weather. And then we try to predict when trucks will be needed where and when to unload what containers. Also in the ports, we have a tactile IoT use case. It's kind of about this guy up there who's remote controlling automated guided vehicles that operate in potentially hazardous conditions. So that's like this, for example. And here the idea is that you can assist those vehicles and perform certain tasks that require human intervention remotely using a mixed reality cockpit and haptic gloves. So these are the use cases and they define kind of what we want to achieve in the project. Now the question is, how can we derive an IoT architecture from that? And the key principles that we apply in the project are that we want to exploit real-time positioning and tracking of basically everything, all the assets that are being moved and also some part of the equipment, have low latency and reliable communication for remote controlling, and of course also to communicate sensor data. And the key part then is that we want to make all these data streams accessible in a combined way. And this also is the introduction to the sixth use case of this project, which is about ecosystem integration. And here we basically aggregate all the data and all the informations in order to perform some kind of data virtualization and also preserve integrity of the data so that we can have applications on top that serve the end users, and they can operate on all the data regardless of what kind of individual solutions there might be at the bottom in those various use cases. Okay, so what does the architecture now look like? The architecture is a layered architecture, and that's at least the way how I explain it now. And we have 4 layers. At the bottom, we have things, then there's the network layer, data management, and applications and analytics. At the things layer, we of course have our IoT devices, and specifically I'm talking now about those that we have in the project, which is, for example, those factory robots. We have vibroacoustic sensors that are connected to a fairly new and secure by design compute module, which is performing this processing or helping with the processing to figure out when a train has a problem and needs to go to maintenance. Then we have, of course, sensors in containers and even more sensors in the port. And all these devices become IoT devices when we connect them to some kind of network. So in terms of network, we have one partner providing a 5G modem and working on that front. 5G is also used for the more tactile factory automation use cases for the HEVs and in the port and so on. But we also consider other kinds of connectivity because those sensors, they are very diverse. So we have, like, for example, cellular IoT, non-3GPP modems. We have completely different ones, like even some kind of network, mesh networks are being considered. We also have in the project a partner that is working on making radio access, actually the PHY and MAC layer, more flexible in the sense that you can adapt the parameters that the network use for optimal performance and even for some security goals. And all these modems, they of course connect to some kind of network, some kind of radio access networks. They exist for the various technologies being used. We focus in the network backend, you could say, or backbone on 5G and have some activities there. We also have, of course, multi-access edge clouds deployed where we can do localized processing very near by the actual devices. And we also work on integrating satellite technology into 5G networks. There's another box in the network that I will be talking about later. The final one in this layer I want to mention now is the Smart IoT Gateway. And the Smart IoT Gateway is, of course, some part of network device in the sense that it has lots of connectivity options. So that's why it's a gateway, but it's also performing a certain amount of data processing. And that's why in this architecture it also integrates tightly or is interfacing with our data virtualization layer. So what is that? That is actually the key component, or one of the key components of the ecosystem integration efforts. So the idea here is that we have all these various machine-to-machine platforms that receive their data from their respective IoT devices. Sorry, okay. They are from the devices and make them accessible using a coherent interface to the top. Other applications or other external data sources like port information systems are feeding in there as well. So we can have factory operations that we can better monitor using all the available information. Even more important, this is in the port use case, where we optimize port operations and yeah, all kinds of visualization and monitoring you might imagine. So we also have smart and tactile IoT apps that I mentioned already, and they are basically for these yeah, HAV use cases and the robots. The difference here, and that's also why the color is blue and not yellow, is that here we need high reliability and very low latency, whereas for the others, for the yellow connections, it's yeah, at least the latency is not so important. So we can afford feeding them into the DVL and aggregating them and so on. But this would not be a project, of course, if we were not working on integrating all those technologies better. So one of the cross-layer technologies that we apply everywhere and integrate is AI and machine learning. So we use, for example, this data that is provided from all the sources via the DVL to optimize factory operations, or at least monitor them. We try to predict what is going on in a port in order to optimize the operations there. But we are also using the data from the DVL to optimize part of our own infrastructure. And in this case, this is the missing box here, which is the management and network orchestration component of the network. And here the idea is that we use the data that we have about what kind of devices exist and what they are doing in order to optimize assignment of network slices, for example. So we optimize resource usage in the network and better guarantee low latency guarantees, for example. We also do this at the edge, as I mentioned already. So there's this machine learning approach for detecting train axle defects. The other cross-layer aspect is security and privacy. And here we have a DLT-based solution. It's Trustors, which is itself based on Hyperledger Fabric. And here the idea is that all the data that flows through the DVL about all the supply chain events gets also recorded in DLTs in order to have a proof of existence that some kind of event has occurred, so that you can solve disputes and there's no confusion about what happened to this container and why is it now damaged, that sort of thing. It's also feeding into the applications, giving them those security guarantees. And in the project, we actually store this in multiple DLTs. So we kind of establish interoperability. So interoperability is one of the overarching goals that we have here. Of course, there's also security in the network. There's also security at the device level. And the device level is actually one aspect I would like to dive into a little bit more, because this is actually also the area where I work in. And this is about this compute module there and how it's communicating with the cloud. So what we at the Barkhausen Institute are developing is some platform or some architecture for constructing the computers that are part of every IoT device. And the focus here is actually on configurability and security and also low power. And the idea is, so we currently have this on an FPGA, and the idea is that you connect some sensor, and the goal here, especially in this use case about the train axles, is that we want to communicate information about there's a problem with this train axle to some control center. And here we have a lot of security problems, potential security problems at least. So this is why we are using transport layer security, for example. But the idea and what our platform now enables is that within the platform at the hardware level, we can separate those functional components like the sensor interface. We can separate this from the network interface by having hardware support for routing communication between different tiles of the chip. And we use this together with root of trust technology to enable remote attestation. So you not only get information about or protection of the communication channel, like integrity and confidentiality, but you also know that you're talking to the correct control center and the correct sensor. So that's the idea. We also have some activity with regard to integrating the flexible PHY MAC there, but I'm not going to talk about that in detail. So that's that's the overview of the ingenious architecture. I hope I'm not over time too much, and I think there's still some time for questions. Thank you.
Thank you very much, Karsten. I don't know if there are any questions on the chat. If not, I would like, just out of curiosity, to ask, since this is about supply chain interactions, right?
Yes.
How do you handle the data compatibility problem, right? Especially since I saw that on one of your slides, that you have also different operations, right? Different verticals, which can be also interconnected, of course, right? Like manufacturing with port operations. But how do you really handle the data interoperability in the
Okay, so
is there any standard model or a way to define compliant models?
I don't know if you can see the mouse cursor moving. Probably not. Okay,
we can see it. We can see your cursor. Yes.
Oh, okay. So the idea is that so part of this is happening at this data virtualization layer here. So of course, all these different end-to-end platforms, they have their own data models potentially. And the goal of this one is to basically understand whatever these guys down below here are talking about and translate it into a common data format that we can use at the top. So that's the general idea. So we do this here at the DVL level, but we are also doing part of it in the Smart IoT gateway that we, for example, use in the ship use case with the container. Here we also perform buffering and translation of data formats and so on. So that's the basic components where this is taking place.
So there is this is a process, let's say, semi-automated, right? So
yes. So
it's not that you've got a number of data formats that if I give my data in this format, then I am done to using your platform, right? I need to do some extra work here.
Yeah.
Mapping and things like that. Okay, clear for me. Thank you, Karsten. I don't see any other questions or feedback on the chat, so I suggest, I don't know, that if you can stay around till the end, then we can, thank you very much. So then we can move to Professor Sarianidis and Terminate project. So Panagiotis, the floor is yours. Please feel free to introduce yourself and your project and then give the presentation.
Thank you, John. I hope you can see my screen. So thank you for this excellent event. Thank you for the invitation, the organization. It's quite important to discuss on these common projects and to see what is what are the trends of the next generation IoT architectures. I'm Panos Arianidis. I'm an associate professor in the University of Western Macedonia in Greece, and I'm the project coordinator of Terminate, a next generation IoT reference architecture for the ICT 56 call. And I would be very happy to present you the Terminate project and our view, our experience, and some thoughts on the proposed next generation IoT architecture of this project. So here you can see the identity of Terminet and the consortium, consisting of a balanced form, having industries, universities, research centers, and SMEs. We are currently on, we're just closed the first year of the project. And I'm happy that I can share with you some first feedback coming from the use case, the pilot sites we have here. But first, let us see our common problems, issues, and challenges we all share in these projects, like the lack of resources of cloud computing to cover real-time applications. To my perspective, this is the main challenge here, to open the market for new products, for new frameworks, for new tools, and new companies, new business in the market of next generation IoT. And for having this new market, you have also to provide the requirements, to address the requirements for introducing, inaugurating new kind of business, like remote surgery, AR environments for training, precision agriculture, having AR and VR approaches and things like that. So in order to open this market, we have to go down and bring intelligence at the edge, and bring intelligence close and near to the device, near to the physical layer here, to the IoT devices, to the devices that are capturing and processing the information coming from the IoT infrastructure. So we need to enhance the IoT, to combine smart technologies, also to provide security and privacy by design. That's quite important also. And as John mentioned before, to provide solutions for covering interoperability. Since one of the major problems, and that was the the motivation for this project, was that in smart farming you may have a collar running on LoRa, and you may have also a sensor running on Sigfox, and these two devices cannot cooperate together. So we have to provide solutions and approaches to resolve and open the way for addressing all the current challenges coming from down near the infrastructure, going up to the current state of cloud computing. So these are the 10 primary challenges. I can say that the most of them are common to the other projects. And let me focus more on the objectives we have. So beyond providing a new reference architecture and a new solution, a new approach here, we try to evolve a lot the SDN technology for providing two main things. First, to resolve the interoperability issues, and then to provide high level of visibility through all the layers of the next generation IoT approach. Then to move AI and intelligence to the lower levels, also to design based on attestation, modeling, and enterprise level privacy, new solutions in a vertical layer. You have also available tactile IoT models for reducing mostly latency related, sensitive to latency applications, and to provide, foster, and open the market. That's important here, to open the market, to make all these devices and products in a low cost available to the new next generation IoT market business. So in 4 main steps, Terminet includes SDN and NFV solutions for resource allocation first, interoperability second, and also visibility to facilitate and foster all the security things we have to do also in the next generation IoT, along with privacy by design, by using federated learning. Federated learning is quite good solution when it is used in an appropriate way, and it also gives the opportunity to protect the data coming from the lower levels, and allowing the transaction only to models between the different users, the different levels, and the different businesses here. We go further to AR and VR contextual framework. You know, given that we can have latency appropriate, you know, maybe less than 2 millisecond latency infrastructure, we can support AR VR applications, and AR VR applications are quite popular and very friendly to people and to stakeholders that are not still yet, you know, are not yet part of this business. So it's quite important to open the way for newcomers, new stakeholders here, new applications, and I think AR VR could open the way for such an introduction. And in the upper layers, it's not show upper. I think it's more the vertical, but we support also a trust environment. We support trust environment, supply chain, and in production lines by having a good view of failure prediction and predictive analytics for having some advantages also in the supply chain in general. So here you can view in a high level the proposed terminate architecture. Starting from the bottom layers, we have, as mentioned before in the other projects as well, that's something common. We have the physical layer where the IoT devices, the actuators, the gateways, and everything that lies there. What is a main innovation here is that we try to interconnect the physical layer with the middleware layer by using an SDN enabled kind of new layer. So we try to solve here the interoperability and also to make visible to the upper layers the main features of the physical infrastructure. So we pass to the middleware through the southbound APIs, the data coming from the sensors and all the physical devices there. And then the middleware layer, we have some SDN controllers that could, what's the main merit here? They could take decisions real time. So we can have a configuration given not by passing through resets or, you know, due to long delays, but we can have real-time decisions to foster the interaction between the controllers, the upper layers, and the devices, and also to include the streaming analytics and everything needed for filtering, processing, and you know, making all the data coming from the IoT sensors clear data in less time by having also hardware abstraction and semantics. And of course, something also very important here is to provide real-time authentication. So by by plugging and play one IoT and one new IoT device, an authentication protocol takes into ground and makes what is needed to ensure that this is not harmful from the system to the system, and that is safe and compatible to the other devices. And also here, real-time certification is also examined to provide some kind of certification examination that this device encloses the minimum required features and requirements and identities for supporting this new kind of architecture. Then the intelligence layer, and as you know, as you can see, this is part of the edge node. So we are talking still on the real side, near the end user, near the the playground, very close to the playground. So here the filtered data and the filtered IoT data streams, they are used for local training. So one part of the federated learning comes into place here. And we have only local training, so the data coming from the A edge node are not transferred to the B edge node. They are protecting locally, and only trained models are exchanged between the edge node and the upper layers. So we apply here a kind of privacy by design model, and federated learning seems, based on our feedback already, seems to work well here, and to protect the pure data and the streams by exchanging after being encrypted, the models, the global models only. And what is also important here is that this kind of intelligence is not limited. I mean, we can have edge nodes in different domains. I mean, we can have some kind of edge nodes in a hospital, others in a farm, and others in a supply chain. So intelligence could be trained and advanced based on data coming from different domains, different kind of activities. In the platform layer, we run everything needed for optimizing the resources for covering the applications coming from the top. So we manage cloud services as close as possible to the end user. So we try to see here where we can apply this platform as a service layer. But for sure, this is close, as close as possible to the area of activity, to the user of this architecture, in order mostly to lower the latency needed for running the upper applications. So we place physical IoT devices, frameworks, and all the hardware abstraction behind with virtual images. All these kind of visualization is also combined with 5G capabilities, if this is the case here. And the global models come into place. We can share global models without sharing pure data between different platforms. So the intelligence runs there by having optimized resources, and all the decision-making, all the output of this knowledge comes down again to feed the edge nodes and to have better decisions, low latency and high capacity of the applications, and the cloud stemming from the cloud tools and contextual frameworks. And the application layer, we have here first the blockchain toolbox. So this toolbox could be used for applying predictive analytics mostly in the supply chain on production lines, and for example, to have some predictions on some failures, or to come back and see what happened in a failure and to improve it based on this feedback. Also, we have an inventory of new IoT device. That's also very important for Terminate, since here we apply new haptics for supporting use cases. We apply also 3D glasses for supporting and making all these new services more attractive to the end users, and to foster also the business models here. So AR/VR is quite, dynamic in Terminate, and also user panel for the users to monitor the performance metrics, to set some KPIs, and of course a dashboard for controlling everything. And this is the security and privacy vertical layer at the left, where we try to provide security and privacy models, frameworks, and encryption toolboxes in each kind of layer. So in the upper layers, we try to build a network of trust. In the lower layers, we try to apply real-time authentication and also anomaly detection. In the middle layers, we try also to encrypt and decrypt, if needed, also the global models and everything optionally to be exchanged between the layers. So for terminate, what is important for us is to apply all these things per use case approach. So many of these design options could be adjusted based on what is the real problem in real life. So we have 6 use cases, one in smart farming, one in personalized healthcare, and one other in smart lighting in efficient buildings, one other in supply chain in dairy products, one other about group training surgery, remote surgery, using VR technologies in a hospital, and one more in mixed reality and fault prediction in IoT-based critical infrastructure in the energy domain. But let me focus just to give you an example on the smart farming case. This use case is realized in Greece. So we try to to open a new market here and to support new devices, new 20 and 6 devices for crop monitoring, livestock monitoring, better decisions, optimized logistics here. And we use IoT device like wearable collars, sensors, Ori collars, and many type of these things for a use case that we need to to export it as a very attractive and doable use case coming from this new proposed new generation IoT architecture. And what is the result? The result is that the end user here wears 3D glasses. Any kind of activity like the animal tags appears on the cloud, so the end user is able to see all the activity, not only to see, but first to see all the activity coming from the environment. So by using LoRaWAN and beyond, that's an example here. That's an indicative kind of communication. The end user is, and the farmer here, the producer, is able to see things that was not able to see until then by using a very simple device like glasses. So he's able to track all the animals, to have advanced information coming from the animal health, or to take some decisions, some suggestions, for example, for feeding the animals, for taking care some animals that present anomalous behavior, and to select many things that could optimize the supply chain, improve the products, and also reduce the cost of the logistics. So what we can do here, what we do, this is feedback coming already from the use case. We can have many, let's say, edge nodes, local training at the edge nodes. That's a very indicative example of applying the federated learning approach. So we train the global models, and we can have decisions backwards about, for example, the milk quality, the milk price, the production line that gives us the milk, some kind of individual decisions. And further, if we put many edge nodes, not only on the farms, but also in the supply chain, we can have a variable set of global models, and these global models could also support decisions in many other levels, in a more deep level, by providing conceptually mutual decisions, and this could be go back and forth and improve the final product, and as I mentioned before, to reduce also the logistics, so as to make all this business attractive to the end users. That's important here. The technology appears, it's quite mature in many cases, quite mature, and what is important is to be adopted by the end users. So I would like to thank you for your attention. I would be very, very glad to discuss further on these very, very interesting features of next generation IoT. Thank you.
Thank you, Panagiotis. So for the animal use case, you do not need 5G, right? You just need LoRa, right?
Yeah, that's important. We have to provide, reference architecture for supporting use cases, even though 5G is not there. So we have to support the operability and to make it doable, even though it's not connected to a high capacity kind of.
If it is a very big farm, is there also a chance that you lose connectivity on some points with the animals? If it is a really big area, or this is not a problem.
Yeah, by using LoRa technology, the demand, let's say, the level of data is not so demanding, it's not so strict. So you can support data coming from the IoT devices by using low data rates. So this is doable. No 5G is needed. But if you have 5G, you can support more things. But this should be on a use case level. It should be decided on a use case level. So we have to be able to play with 5G enabled environment and not 5G enabled environment.
Okay, great. So I think we are just in time for a short break. So we can take 5 minutes break and be back 1:25 for the next presentation. I think it's okay to have a short break because today's session is a little bit lengthy, at least more than usual. So yeah, I think I can ask Carlos. Yeah, if you want, you can project your presentation, prepare your slides, and I think in 5 minutes, and we'll be back right now in 8 minutes. Okay.
Okay, perfect. I will be preparing the slides.
Very good.
Okay.
Okay, and I hope, yeah, I see our audience is still connected, still online, and I hope that everybody will become more active in the questions. And I would like to give the floor to Assist IoT and the coordinator himself, Professor Carlos Palau. Carlos, please feel free. The floor is yours. Please introduce yourself and your project, and yes, deliver the presentation on the architecture. Thank you very much for your presence.
Okay, thank you, Yanis. Thank you for inviting me to make this presentation. I'm the fourth in the row, and all the colleague projects have made wonderful presentations, and I find a lot of common things regarding the different projects. So I'm Carlos Palau. I'm professor at Universidad Politécnica de Valencia, and I'm the coordinator of Assist IoT. Assist IoT is one of the 6 RIAs that were funded under the ICT 56 call, and these are the 15 partners that are participating in the Assist IoT project. We have university research centers, we have big industries, we also have end users and stakeholders, and also big companies like Ford, Cranes, and Orange. The idea behind developing Assist IoT is that we want to try to avoid the traditional centralized IoT architecture's lack of capabilities, and we need to handle new requirements of new applications that we want to deliver. And mainly, one of the things that we aim to provide with Assist IoT is to be able to provide a near real-time reaction close to the event try to make automatic decision close to where the things are happening, and try to provide with all of this intelligence close to the edge, or close to the different devices. So what do we aim? We aim to provide and to create a blueprint decentralized architecture for next generation Internet of Things, and we will introduce, as I will present later in the architecture, different enablers, different components that will be providing different capabilities, different functions inside the architecture and the deployment of Assist IoT. So our idea is to, with the blueprint architecture, with the different components, the different elements, be able to allow the different stakeholders, the different entities that are participating in the project, the newcomers that are coming as third parties, and later on the whole ecosystem, to be able to overcome the different market barriers that may appear and try to provide new disruptive business models all around the IoT edge cloud continuum and the different elements in which we can deploy the developed component. So this is the vision that we have. We will be going through the different elements later on in the different slides of the architecture, but the key aspects of the Assist IoT vision is we want to provide a decentralized architecture. I mean, an architecture that can be deployed in different points of the IoT edge cloud continuum. Provide interoperability and hyperconnectivity with the different elements. We are using 5G in one of the use cases. In other ones, we are using LoRaWAN. So we will be talking about this. Provide context awareness, because this is something that we consider important, and provide distributed and decentralized intelligence in the different components that will be constructing what will be the deployments. Data privacy and data protection and data privacy are a must, and we are providing inside the project. One of the outcomes will be a DevSecOps approach methodology provided for the next generation IoT. It will be provided as a white paper and a cookbook in order to be used by the different third parties and the newcomers, and different interfaces based in augmented reality in some cases for allowing collaboration and interaction. So we will see that we will have different horizontal planes and different vertical planes in order that will be composing the different elements. We have named the TC, the technological components that will be deployed. We have a full list of these technological components, and the different building blocks, the technological components and the position in which they are in the layers will provide or will create what we have developed in the architecture and specified in the architecture. So the main and overall goals, if you see in the center, the main goal of Assist IoT is to provide a new architectural distributed approach for future IoT, and around it we will be developing a new accessing of contextual data, new kind of artificial intelligence application, addressing the needs of different verticals. We try to be as much agnostic as possible, addressing scalability and flexibility, as we will see later on in the containerization and virtualization elements that we have considered as key aspect of Assist IoT, and try to transform the existing IoT solution into smarter, more secure, trustable, and be as more efficient as much efficient as possible. So the architecture that we are proposing in Assist IoT will be multi-plane, will be modular and adaptable for the different deployments, will have scalability as one of the key requirements. It will be decentralized from the point of view that we aim to be able to deploy the different components that we are developing in Assist IoT in different elements of the IoT edge cloud continuum. For example, in the far edge, in the edge, in the cloud, if possible in the different devices, although with the technology that we are having, little smarter and bigger devices, and try to provide human centricity all around, and be able to work on a smart network infrastructure. We are working with SDN and FB. We are introducing 5G, mesh network, LoRaWAN, different elements. So everything with the goal of transferring intelligence closer to the edge, as close as possible, and try to, this will be one of the results that we will be providing by the end of the project, trying to provide innovative business models bringing this intelligence to the edge and avoiding the typical business model related with the cloud. So in Assist IoT approach, we have the horizontal planes that will provide different capabilities. We have a structure. We have analyzed the different state of the art. Some of the things that we have analyzed have already been commented by Yanis in the first presentation, and we have grouped them in application and services, data management, the smart network control, and device and the edge. So with the possibility of introducing new planes, if we want to decouple any of them. And in the vertical planes, we will be providing the different cross-plane, cross-cutting technologies in the different elements. So the core enablers of the architecture will be located in the horizontal planes, and the transversal enabler will be the specific functionality to provide some cross-layer, cross-plane technologies. So the core enablers will provide innovative interaction to focus on human centricity. They will guarantee data governance, and they will provide and facilitate distributed artificial intelligence. So the vertical planes will have the potential to provide more modularity and more adaptability to the different deployments. So in the same way as we have been discussing before by one of our colleague projects, okay, the idea on how we have built up the Assist IoT architecture, we have defined the different requirements, starting from the different use cases and scenarios particularities, with discussions with the stakeholders, analyzing the state of the art, having different discussions with different entities, and coming from the different technical domains, we have obtained different constraints, different technological consideration, and this has been bringing what we have called, or what we call in the architecture, the different enablers description. So if we start with the pilots, I don't want to start all the process. I want to go directly to the architecture, but this is the three use cases that the three pilots, the three use cases that we are having in Assist IoT. We have one related with cohesive vehicle monitoring that we are working with Ford in Aachen, Germany. Also one related with port automation and container movement that we have in Malta, in the Freeport terminal of Malta. And another one related with smart labor risk prevention in a construction environment that is being handled by Mostostal Warszawa. The three pilots that actually, the one related with the cohesive vehicle monitoring has been divided in two sub-pilots after discussion with the external reviewers during the technical review and analyzing the different aspects in order to provide a better validation of the architecture. In the port automation, we have the idea of having different flexible container handling equipment and the terminal operating system deployed, and the connectivity, it has to be flexible. It has to provide intelligence close to the events are provided. And we have different kind of data access methods. For example, in the smart safety of workers, we need safe private data collection and efficient and fast near real-time discovery of hazardous situations. In the case of cohesive vehicle monitoring, we are working in two lines. One, inspection and documentation of exterior of the vehicles, for example, for rental companies, and additionally, inspection and documentation of the vehicle engines, working with far edge nodes deployed in the cars. Ford has kindly lent us a car in order to introduce a far edge node connected to the ECU and work with the let's say the different aspects and parameters of the engine, and we are working with this. So the high level vision of the architecture is we want to achieve a high level of abstractions, and we will be lowered down towards different concrete deployments that we are having. It will be, the idea is that it will be applicable to many domains and different kind of applications. It has to be flexible, decentralized, and modular. And here we will be having the device and edge plane, the different components, the smart network, the data, and the application service plane, with the vertical planes providing the specific capabilities. So if we go a little bit deeper into the horizontal planes, we will be analyzing the first building block, the first functional blocks that will be providing the implementation of the different enablers. For example, we will be analyzing later on, because we have selected one in order not to extend too much the time. For the part of the smart network and control plane, we will be seeing the different enablers that we are developing in order to fulfill the different functional blocks in the horizontal plane. Sorry. So the idea is to decompose the different functions per plane. So we will be having this view as what we call the functional view. Later on, we will have it per node, because the idea is to have a kind of virtualized environment that allow us to, with independence of the hardware, to provide the deployment of the different enablers, containerized enablers, having the network, the storage, the different the hardware infrastructure, and the protocol abstraction layer to be working with it. Then this is what we call the deployment view, that it is what we will be having when we go to the different pilots in which we are working. We will have the cloud nodes that we will, the edge node, the far edge nodes, and the different, let's say, hierarchical components that we are having. And the access networks that we are talking about, 5G, TSN, Wi-Fi, whatever network we want to use. So the idea is to have a set of supporting figures, the functional view per vertical and per plane, to have the service deployment, the set of enablers that will be orchestrated in the different elements, and with this having the conceptual architecture. So this is just a parenthesis within the description of the architecture, because the idea is that when we have one of the enabler, every enabler will be accessed through an open API. So the idea is, if a user is working with an enabler, will be able to access to this open API, and will be able to access to the different components. Actually, this is the information that we have provided to the third parties that are going to apply for the open call, and then everything will be accessible for them without knowing how the internals of the different enablers are being developed. So following this, we will have all the enablers will be encapsulated. So in order to be able to add scalability to the different deployments, resiliency to the different interaction, modularity, and the possibility of redeploying the different enablers in a different hardware or in a different environment after it has been configured. So our idea is to be as much flexible technologically as possible. So this is, for example, the different building blocks in one of the enablers, one encapsulated enabler, for example, the one related with artificial intelligence that we are currently developing. There will be a link with the function service in the horizontal plane, and additionally there will be a link also with the different verticals, for example, regarding interoperability and so on, if any of them needs to have some connection with this enabler. The idea is not to expose internals, so everything will be encapsulated and will be containerized, okay? And the possibility of an enabler being able to deal and discuss with other enabler, orchestrating the different tasks. For example, if artificial intelligence on the edge need to interact with the enabler of artificial intelligence in the cloud, it will be orchestrated. And additionally, for example, the artificial intelligence enabler in the edge needs to, for example, use the enabler of graphical representation, it will be available to be used by the enabler. So the idea is to have an easy deployment. Here is, we are going to use Kubernetes, and the idea is to be able to orchestrate the different containers, be able to provide different interface channels for dialogue between the different enablers, and try to be scalable and resilient by design. So once we have the different encapsulated enablers, the idea is to provide in the architecture different composable services with a link between the different enablers with different components inside of it, and be able to by design provide scalability, composability, redundancy, and so on. It will be ready for the edge. It will be ready for constrained devices, and it will be ready also to be deployed in the cloud. So we want to build, or we are building on open standards, and we are, let's say, using a huge community effort and trying to contribute also to this community effort, to these open source communities regarding Assist IoT. So the idea is that we are working right now in essential and complementary enablers with the possibility of growing and building new enablers separated from the physical layers, easy adaptable to changes. So the idea is to be able to develop one enabler that can be deployed in the different elements of the IoT Edge Cloud continuum. So later on, the Assist IoT pilot deployments will be specifically configured and composed for the required function in the different pilots. So regarding the part of the network, we have selected the smart network and control plane. In another presentation, more in advance, we will be selecting another one. But actually, this is one of the 4 horizontal planes. The idea is to provide these novel enablers, and the enablers that we are developing in the different planes, they have to be self-scalable of resources. Okay, in order to among the different nodes in the deployment of the specific pilot, we are trying to be homogeneous, standardized, and as user-friendly as possible. And for example, in the case of the network, providing seamless deployment of network functions, easy connection of, for example, in the case of the network, we are working with VPNs over Kubernetes assimilable environments, and provide traffic classification using artificial intelligence for this traffic classification within the network. So this is, for example, the way of doing the self-scalability of resources in an horizontal plane. Try to provide different metrics, different ways of measuring how things are working in order to be able to control the different resources that are being used. This is another enabler that is related with the network function virtualization, and one of the components is related with a network function virtualization orchestrator, okay, based in Mano. Okay, it has an abstraction layer. We are also working with kubectl proxy and the possibility of providing different expansions. For example, this is another enabler that is related with own VPN connections in order to provide security between different containers, providing a health checker, also load balancers, and using as technology WireGuard. Okay, so this is another possibility of another enabler that can be we have developed and will be can be used by the third parties. And okay, this is another slide. And the possibility of providing also traffic classification using a knowledge base with a training module, and in order to be able to classify the different traffic that we are having in the different deployment for different utilities. So in the different pilots, okay, we have analyzed for the different planes the key functionalities that we are requiring. For example, if we select pilot 2 that is related with port transportation, we need a smart IoT devices and gateways and edge nodes. We also need a self-contained network because, for example, in this case, we are not going to use SDN in this pilot. We would need semantics in order to provide interoperability and data governance for the different elements. Augmented reality, because one of the application that is going to be handling containers, using container handling equipment with augmented reality, and different elements like, for example, support for third parties if we want to integrate with different elements. So the conclusions regarding the architecture, we have published the architecture in deliverable 3.5 of the project. There will be 2 more versions that will be released. Okay, some of the work that I have presented today is not included in deliverable 3.5, will be included in deliverable 3.6. Okay, in which there will be a link with a high-level architecture of IoT and also with 3GPP MEC. And we will be providing in the integration of the architecture, virtualization of components, microservices, data autonomy, and orchestration of different enablers in order to provide, let's say, an execution in the cloud, in the IoT Edge cloud continuum. So this is Assist IoT. Follow us. We have already launched 1 week ago the first open call of Assist IoT. So all the information you can access there if you want to access the information of the open call, and also there will be some the proposer package in which there are more information about the different enablers available and different aspects. So thank you very much. If you have any question, I don't know, Yanis, if I have been on time or I have extended too much.
Yes, you are very punctual. You are perfectly on time. Like
thank you.
Like
thank you. Thank you, Jan.
Actually, there is some time to take questions. So as far as I understand, from seeing all the projects, right? This again, like IoT engine, right? So it's not a a big fat thing of how to do things, but it's rather a series of patterns, right? That you can pick up, right? What you want to do, probably because to do all these things that you need to do in Assist IoT, right? You need multiple systems, right? And different architectural blueprints. So I found this, the concept, right, not the architecture, a little bit similar to IoT engine. Just trying to spot, the commonalities here.
No, of course. This is one of the things that I like of this presentation. Actually, I have seen some similarities with IoT engine, and also some aspects, for example, for the different layers, and also with Terminet. But these are things that we already spotted in previous presentations. So actually, you are right. The idea is to be able to provide different, let's say, connection between different enablers and being able to deploy them containerized in different elements in the continuum. So if we are able to provide the containers and the execution of the different elements, for example, on the edge, then we will be able to create new business models. That is something interesting for different companies. And if we need further execution, we move elements, for example, to the cloud, or even if needed to the far edge in order to be able to execute different elements. So I agree with you, and there will be, I think, in the next projects to come more similarities. And I think this is one of the works that you in EU-IoT are doing well. Try to spot these commonalities and probably in the near future be able to align different works in the projects.
Yes, true. We may write a very short white paper with presentation of all this. It would be useful. However, since we have 1 minute, could you also say a few things about the open call? So what you invite, because there are some people connected that might be interesting. You are inviting applicants to do what? To build applications or to build some module of your system? What you are inviting companies to do?
Actually, we are going to have open call. What we are inviting is people to validate the different enablers, building different applications, and be able to work over what we are developing in Assist IoT. Let's suppose, for example, for the port environment, if anyone has an application, for example, for a smart location of containers inside the container terminal, adapt the application they have in order using the different enablers that we are having or we are developing in Assist IoT. So right now we are focusing in the pilots that we are having, and in the second open calls we will be extending to new verticals. So that's the idea about from the open call.
Okay, very good. Thank you, Carlos, for
being
here. I know you are a very busy person, so thank you for joining today and giving the talk.
Thank you.
Maybe it's time to go to our next speaker in IoT, Konstantinos. The floor is yours. So please feel free to introduce yourself, to introduce your project, and give your presentation.
Thank you. Thank you. Let me just share my screen. So I'm Fisarachos Andreas. I'm the CTO of Sphinx Analytics. We are responsible for the architecture in the IntelliOT project. I will share this presentation. Actually, the second part of this presentation will be provided by Sumia, our colleague who's working with Eurecom, because we also want to highlight a bit the alignment of the IntelliOT architecture with the W3C Web of Things, let's say, landscape. So this will be the second part of the presentation. Let me first talk a bit about myself. I mean, we at Sphinx Analytics, we're basically working on security assurance and certification. We have significant experience also on research projects, but our tool set, let's say, is quite diverse. I mean, we have specific platforms like our security assurance platform. We're also working on cyber agents, and also a big part of our work is on security operations center. So not just research, but also some hands-on security stuff as well. As I said, in IntelliOT, we are leading the architecture. We recently released, like a month ago, we released the first part of the architecture that you get to see here. But as the project goes on, we will release one more final version of the architecture, getting feedback from the first assessment that we will do in a couple of months. So IntelliOT, intelligent, distributed, human-centered, and trustworthy IoT environments. And I will talk a bit about the concept. We have three pillars, more or less, in IntelliOT, that is collaborative IoT, human in the loop, and trustworthiness. You will see this also highlighted in our architecture in a couple of slides on. We have three use cases: agriculture, healthcare, manufacturing. And there's a number of technologies that you will hear in this presentation, like 5G, distributed ledger, AR, VR, tactile, and so on. Our project started in 2020, and we will be running until 2023. You see some of our 13 partners in the bottom, in the footer, with the different logos. They're mostly, we have partners from the industry, from academia, SMEs. So again, let me talk a bit about the vision. Our vision is to develop a reference architecture and a framework adopting this architecture to enable IoT environments for semi-autonomous IoT applications that are intelligent and that can involve with human in the loop. That's an important part of our vision. And also, we want to make sure that whatever we deliver is with built-in security, privacy, and trust. I will only briefly mention the use cases because I don't want to focus so much on the use cases, but on the architecture itself. So we have an agriculture use case where we have a smart tractor interacting with drones, with the field, and so on. We have a healthcare use case where we have wearable devices and patients with cardiovascular disease that we monitor, and we try to assist in the patient management. And then we have a manufacturing use case where we have a plant operator handling robot arm and other devices used for engraving, for example, again, in an intelligent manner. And in all cases, you see there is always this human in the loop. That being said, the three pillars that I would like to talk a bit more of IntelliOT are collaborative IoT. So how can you enable autonomous or semi-autonomous agents to work together and carry out tasks, let's say, tend to a farm field, tend to a patient, or manufacture a specific piece that needs to be milled or something. Then there is the element of the human in the loop. What happens when the devices, these agents, are not able to carry out the task autonomously? Perhaps they have not been trained to deal with a specific situation. Let's say a tractor does not know how to go through an obstacle. or a milling machine doesn't know how to handle a specific component or material that is shaped irregularly, for example, then you need the human to do the work, and the next time the appliances will, the agents will hopefully be able to do it themselves. Human in the loop is also important for safety and trust reasons, especially in the healthcare use case. It's not, the technology is not in the let's say at the stage right now where you can say that you can have automated treatment of patients. It's very important to have always a doctor overseeing and having the let's say the last word in the interventions that you want to have in the patients. Then speaking about trust, we have a dedicated pillar in IntelliOT, which is the trustworthiness pillar, as we call it, where we try to make sure that all these concerns about trust in the AI, trust in the underlying components in the network is provided for IntelliOT, but ultimately also for the application where IntelliOT is used in. On the right-hand side, you can see a high-level logical view of our architecture. We have 5 core component groups. So starting from the top, we have the collaborative IoT enablers. That, as I explained, are used to provide this cooperation with various autonomous entities. We have the human in the loop enablers. Here we have technologies like AR, VR that allow the human to effectively and efficiently interact with the infrastructure. And then we have the trust enablers like security assurance, DLTs, and so on. Below that, we have what we consider some core enablers of this core vision. So computation, communication, infrastructure, and its management and orchestration in a dynamic manner to support the above 3 pillars. And then at the lower layer, we have the use case deployment with use case specific components. Going into more details, I will try to be a bit brief. At the heart of the collaborative IoT enablers, we have what we call the HyperMass hypermedia multi-agent system, which is a system that kind of reacts to the end user goals and let's say orchestrates the whole carrying out the task that the user has specified. Here, this is a key component where we are linked with W3C Web of Things thing description and thing description templates. We integrate procedural knowledge, so agent plans to carry out the tasks, and so on. We will talk a bit about W3C more and our alignment with W3C in the second part of the presentation. And we also have, I've seen this also in some of the other colleagues, some of the other projects that have presented before. We have federated learning to support the applications, be it the healthcare application, the manufacturing application, or the agricultural application, allowing us, of course, again, to exchange only the models and not to exchange any private sensitive data. In the human in the loop, we have the goal specification frontend, which is meant to provide an easy way for end users to specify the goals we mentioned before. So let's say plant this wheat field or create, a piece of aluminum that looks like that or something. And of course, this interacts with hypermedia mass to get these plans out to the underlying devices. Then we have HMI capabilities, leveraging virtual reality and augmented reality. We also have a stylus pen to provide a more feedback-rich environment for the humans, for the human operators. And of course, these are supported, as you'll see later, with the necessary capabilities at the network layer, like low latency connections to enable this, obviously, application. At the trust layer, at the trust pillar, as we call it, some key enablers include the security assurance platform, which provides like an aggregated real-time view of the security and privacy posture of IntelliOT and the deployment where it is running. We have also DLTs and smart contracts. This is based on hypervisor fabric that another speaker mentioned also before. So for auditability and accountability, this is very important, both in for example, in the healthcare use case, to provide the needed evidence about the certain actions that took place regarding the management of the patient, but also in other use cases as well. For example, in the agriculture domain, to have in a smart contract coded the different terms about using, for example, a smart tractor that you have rented for a specific job. So service-based models that are now becoming a reality. We also have some advanced intrusion detection systems based on trust, and we also apply moving target defense mechanisms where we adapt the system both at runtime, even when something is not going wrong, just to make it harder for the system to be profiled by the potential attackers, but also when an attack is detected, to trigger defense strategies that would allow the mitigation of the attack and isolation of the attackers. Then we have, as I said, the infrastructure and network enablers. At the network layer specifically, we have, obviously we're relying on 5G networks, so 5G MEC, vRAN, B2B, and a private 5G core, but also this is developed in tandem with deterministic time-sensitive networking technologies to allow for, as I said, to support these time-sensitive applications for that, especially the human-in-the-loop interfaces are requiring. So, for example, when you have to remotely operate a tractor, or you have to remotely operate the robotic arm to make sure let's say the quality of service properties are there. Then at the lowest layer, we have the use case specific deployment. I have some indicative components. So for example, in the agriculture, we have the camera, we have the tractor controller, we have a drone with its own camera. In the healthcare use case, we have a smartwatch, thermometer, oximeter, blood pressure monitor, weight scale. These are all connected. We have healthcare specific AI models. In the manufacturing case, we have the robotic arm. As we said before, we have also a milling machine and with the associated controller. So all these use case specific components are for us in IntelliOT are at the lower layer. With that, I think I can pass the ball to my colleague Sumia. Sumia, are you here?
Yes, I'm here.
Yeah.
Thanks a lot, Konstantinos. I will take over. So let me share my screen. Maybe you have to stop before I can share. Thanks. Unfortunately, I do not have a camera in my desktop, so you'll not be able to see me, but hopefully you all see the screen. So good afternoon, everyone. I'm Sumia from Eurocom, and I will be then talking about the rest of the presentation on alignment of the IntelliOT components with W3C Web of Things. Now, as you know, W3C is the main international standards organization for the World Wide Web. And inside W3C, the Web of Things, or what initially started as an interest group some years back, and then a working group was formed, which is still continuing working on different aspects of discovery and other things. IntelliOT partners, including Siemens, Eurocom, as well as University of St. Gallen, have been involved in what activities since the beginning. So it's quite natural for us to give the presentation on the alignment of the project's architectural components with the Web of Things. Now, before I talk about this alignment, I'm going to describe some of the aspects of such as what is about, the concept of web thing description, affordances as a background, so that it becomes easier for you to grasp when we talk about the alignment between the architectures of both the world. Now, The idea behind Web of Things was to counter the fragmentation in the Internet of Things by utilizing as well as extending the existing and the standardized web technologies. So by providing standardized metadata and other reusable technologies, technological building blocks, what enables very easy integration across IoT platforms and application domains. So our focus here is always on describing what exists rather than to prescribe what to implement. So it's rather a little bit different than many other standard development organizations. Coming to the central concept of Web of Things, so it's the thing itself. A thing is basically the abstraction of a physical or virtual entity and could be described by a standardized metadata. So for example, you can imagine a connected light, which is a physical entity. And when we're talking about a virtual entity, so it's basically a composition of one or more things. For example, imagine a room consisting of several sensors and actuators. So the room in that case becomes the virtual entity, as well as its representation could become like a virtual thing. So in W3C what, the description of the metadata, so must be a what thing description, and the consumers must be able to parse and process this description representation format, so which is normally based in JSON. So moving on, I will come to another central aspect in W3C what, so which is the provision of machine understandable metadata or the thing description. So this is where I'm talking about affordances. So ideally, these thing descriptions are self-descriptive. So the consumers are able to identify what capabilities a thing provides and how to utilize these provided capabilities. For example, if I go back to the example of the switch, then how you can access the switch to turn it on and off. A key to this self-descriptiveness lies in the concept of affordances. And in W3C what, so we are defining interaction affordances as a metadata of a thing that shows and describes the possible choices to the consumers, thereby suggesting how the consumers may interact with the thing. So on the right-hand side, so this picture shows you a very basic interaction, consumer thing interaction. Also, in this picture, so you see much more complex interaction. So it's also possible using the concept of what. So imagine, for instance, we have a light switch controlling a number of lights in the room. The thing description of the switch then includes the web links to that of the lights. And such web linking among the things actually make the what navigable for both humans as well as machines. And this basically leads my presentation to WebThing, so which has 4 architectural aspects, as you see on this picture. And they are behavior, interaction affordances, security configuration, and protocol bindings. When we are talking about the behavior for such a web thing, so it basically refers to both the autonomous behavior of the thing as well as the handlers for the interaction affordances. And the Web of Things thing description, it's basically covers rest of the architectural aspects of a web thing. In this slide, the picture depicts the concept of W3C what that are applicable to all relevant IoT applications, covering the device level, edge level, and the cloud level. And this basically fosters common interfaces and APIs across the different levels and enables various integration patterns that you see in this picture. So such as thing to cloud, or even direct thing to thing interaction, thing to gateway, thing to mobile phone, like this. So even cloud federation is possible in the scope of W3C what. So in our project, so we are primarily looking at the edge level. And in addition to that, IoT actually makes full use of protocol binding security mechanisms defined in the what architecture. So in this slide, we are basically demonstrating the abstract architectural alignment of IoT components with the W3C watt. So the architecture on the right-hand side, so Konstantinos has already introduced it in his talk. So the mapping between the WebThing architectural components, which is basically on the left-hand side, with the IntelliOrt's architectural component are basically provided here. So you see a very clear mapping between, so for example, the protocol bindings are basically done here in the edge compute infrastructure. So these are the real devices which are basically talking with different protocols with the components at the higher layer. The security configuration is taken care with the block that is on trustworthiness. The rest of them are covered by collaborative IoT, human in the loop, as well as the infrastructure management as well. If I go into a little bit detail, so all the services in IntelliOrt that might be used by the consumers, so they are encapsulated within the edge apps. So in alignment with the W3C watt architecture, so these edge apps are modeled as web things, and so basically they are providing their thing descriptions as well. And their functionalities are advertised in the form of interaction affordances within the thing descriptions. Konstantinos also introduced how we are utilizing hypermesh infrastructure in his talk. So from the perspective of what? So the agents in hypermesh infrastructure are basically what consumers. So if an edge app is not deployed, so in such a scenario, agents can still be configured to use the functionality of their edge app at the runtime. So to enable this, and in a further alignment step, what we do is that to make use of the thing description templates. You have to note that thing description template has been renamed in the latest watt architecture as thing model. Now, okay, coming back then to the thing description template. So in this case, what we are doing is that in case the template does not provide protocol binding at the runtime, the agent still calls upon an edge orchestrator to provision an edge application and deliver the protocol-bound W3C web of things thing description. So in this case, the edge orchestrator becomes a thing, while the edge app becomes a web thing. So this is basically what I was explaining already. So this is just a quick summary of what I just described. And on a final note, leaving the scope of the immediate consumer and web thing interaction, in IntelliOrt, the interactions between the consumers and web things are journaled using a distributed ledger. So I also provided links to some of the main concepts in Web of Things for further reading. So you have the what profile, thing description, security privacy guidelines, binding templates, although I didn't go into quite details, rather kept the discussion on a very high level. And I think that's it for my presentation as well. So thank you for your attention. And if you have any questions, we'd be happy to answer them.
Thank you very much. So I think one thing that I don't know if there are any questions in the chat, otherwise we can proceed to the last presentation, but one question that came into my mind, again, trying to interrelate these presentations, right? That for the open calls to work, you need to have some clear APIs, right? And I think in your case, I understand that this is one of the purpose, right, of having a well-structured architecture. Could you please comment on this, right? So if I'm applying to your open call, then you need to give me something, right, to build upon. Is it an API or what else?
Yeah, I mean, if I can comment on that, we in the first open call we have two open calls. So in the first open call we are mostly trying to actually enrich our solution in terms of let's say the technological toolset that we have. To give you an example, we would like to have like we have described and we have considered the existence of a drone that let's say in the agriculture use case cooperates with a tractor, but we don't have the in-house expertise in the consortium to have a drone. So if we could get, like, for example, a drone, a new partner that can bring us this expertise, that would be very welcome, to give you one example. Because we have, like, in the first open call, it recently actually ended the open call, and we are now in the process of evaluating the applications. I can say it was very successful. I mean, we are mostly looking at expanding, having some technologies that are integral part of IntelliO. In the second open call, it will be more like what you commented, John, that we bring in new, for example, a new application area to demonstrate the openness of IntelliO, because right now we are still in cycle 1, so we are still, you know, trying to get our components to talk to each other, and, you know, also trying to demonstrate openness and how third parties can interact with the IntelliO.
Even if I bring a smart object, right, to integrate in your project, right, I need some integration point, right? Or
yes.
So, and this needs to be well defined, right?
Yeah, that's the point for the second cycle. We aim to have, for the second open call, we aim to have this level of, let's say, openness that we can also show in the, that, you know, you can come with a new device and there is specific API, specific documentation that you can use to integrate with us. Right now, in the first open call, that was not possible. Also, from a timing perspective, imagine that we only recently released our architecture, and the deliverable and our you know, the open call, the first round of the open call was already running. So we didn't have this.
Not enough. Yes, I understand.
Yes, but it's a very valid concern. It was a concern we also got from lots of the applicants. So okay, yeah. How can I interface with your solution?
Okay, thank you. And did I miss, is there any partner that is member of W3C and maybe pushing anything to standardization? I mean, regarding the last part of the presentation, right? The compliance to the Web of Things.
Yeah. Soumya?
Yes. So from our side, we have identified 2 levels of contributions right now, and I hope that there will be more coming out of the project. So the first one being the 3 use case descriptions. So it will go into Web of Things use case document. The second one being University of St. Gallen is interested to position the hypermass and the entire hypermass infrastructure as I described, and how it relates to Web of Things and how it extend Web of Things. So that would also be contributed to the Web of Things group. And one thing we would adopt from Web of Things into our work is the latest normative standard that is coming out on Web of Things discovery. So if you remember from the description, or I mean, at the bottom layer we have all the different devices, and at the layer above we have different services. So each of them need to discover each other through the thing description, yes, as well as following the Web of Things templates. So that would be one thing where we adopt the standard components in our work.
So you will be having a compliant registry, right? For the
yes.
For the okay.
Yeah.
Very good. And who is actually the W3C member in your consortium pushing this, or it's done independently?
So it's a combination of Siemens, Eurocom, and University of St. Gallen.
Okay. Thank you for the clarification. So without further ado, I think we can go to the final presentation. Really last but not least, from Hans and Vedle IoT project. I think that is also a very interesting presentation about how you can build deep learning architectures for IoT, also touching the ever important hardware issues. So Hans, yes, please, the floor is yours. Please feel free to introduce yourself. We can see already the slides and your project and deliver your presentation. And thank you very much for being with us.
Thank you, John, and thank you very much for organizing this and event, inviting us. It's been really interesting to see what other projects are working on, and I'm very happy to share what we are doing in Vedliot. And as you're saying here, John, we are focusing on deep learning, and that's the main focus. And this talk would be the tool chain for efficient deep learning on heterogeneous hardware, and also then talking about the IoT architecture, which of course is the topic of today. My name is Hans Salomonson. I'm the CEO and co-founder of Embeddle, a startup based in Sweden, focused on efficient deep learning. We are part of ICT 56 as well, and the topic is next generation of Internet of Things. And this is an overview of the project. So we want to attack all the things that could be relevant for making deep learning more efficient in IoT. So starting from the very bottom in here would be the hardware. So that could either be embedded or near edge or something that could be in cloud. And we support a lot of different computing platforms, for example, ARM, x86, RISC-V, GPU, FPGAs, and ASICs. It's a lot of innovation in the ASICs area when it comes to making deep learning more efficient. And that's actually one of the things that we actually do in the project here in the work package 3, the accelerator, where we're developing custom accelerators then for efficient deep learning. Moreover, to optimize this and make the models and deep learning efficient in IoT, we have developed a tool chain for optimization, deployment, and also developed a model zoo so that we can actually evaluate the different approaches both in hardware and software to compare and benchmark against what's available outside and what we have developed inside the project. And we also have these requirements and security that's sort of cross work packages that are looking into our applications and use cases here in smart home, industrial IoT, and automotive, and make sure that the tool chains and the hardware and every technology that we develop fulfills the requirements from the use cases. Yes, and it's for those that are interested in security, we're also making some extension to RISC-V in terms of to make it even more secure. Let's see, it might be interesting for some people here as well that we have open calls. So if you're interested in what we will talk about in this presentation, there will be open calls where you can participate in and apply the technologies to your research or your company. So zooming out a bit on then the deep learning IoT architecture. So deep learning, where should you actually execute the model? So you have different options, right? You can either have it as an embedded system, or you can have its edge, near edge, or you can have it in cloud, or you can actually have it in combination and communicating across them. So we are primarily focusing here then on the execution on the device, and may perhaps not as much focus on as other projects have on maybe communication and orchestration and that thing. We're focusing mostly on the execution of the model in hardware, but then we support different types of hardware. I will come back to this hardware in just a little bit. So we set out then to build a heterogeneous, modular, scalable microservice system. And heterogeneous because it supports a lot of different computing platforms, everything from CPUs, bare metal, FPGAs, neural network accelerators, FPGAs, both embedded and discrete GPUs. And they should then be able to be used in different applications. So not every form factor would fit the same applications, right? So in the project, it's developed different chassis with their internal hardware for different applications, spanning from embedded to cloud computing. So in the embedded situation, you would have perhaps a couple, one or two microservices, and each microserver here could be, for example, a CPU combined with something else like a FPGA, up to very, very dense number of computing platforms, such as 144 in one 3-unit rack system. So yes, and it's modular in the sense that a lot of this technology can be reused. So a lot of the technology that is in the embedded compute platform is also actually in the cloud platform as well. And some of the metrics that we are trying to optimize for then are performance, cost effectiveness, maintainability, reliability, energy efficiency, and safety. So typically, when we distribute the different computing platforms, well, they have different specialization, right? So some of these larger, more high performance, they would be more suited for a cloud system, and others, for example, a TPU from Google, would be more suitable for a microserver or for an embedded systems. So when it comes down to our deep learning tool chain, and this is the flow in the tool chain, would start from this model zoo that we have developed that has models that have a quite good range of applications. Image classification, object detection, semantic segmentation, instance segmentation, and extractor question answering. So a lot of focus on vision for now. We will extend this with more NLP and other models later on. And after, well, then these models or any of these models can then be optimized in an optimization engine. And after that, it will be compiled and into some runtime then that is then executed on this heterogeneous hardware platform described earlier. And the compiles and runtime are typically not developed in the project, but are related to the compute platform that you're executing on. So it could be open source like TVM or more proprietary like TensorRT or RMNN or OpenVINO for Intel. And these are the different applications, what they actually are. So image classification, then it's the probability of what's in an actual image. But often you are interested in more specific than what's in an image. Object detection, for example, then it's trying to find a 2D or 3D bounding box around a particular object, in this case, dog. It's a lot of dogs and cats when doing deep learning. Instance segmentation, then you classify each pixel in the image. So you can separate between the instances. But you can also have something called semantic segmentation when you just have that it's a dog. You don't care that it's instances of dogs. So these are the kind of the most typical applications of vision. And NLP applications, there's a lot of them. We choose to start with one, and that's extractive question answering. So the input then or to the system would be a question and the text, and the system should then extract what the answer is. So in this case, it was who won the Super Bowl, and the system would then detect the start and end position and return the answer. So creating a model, so you might ask, what models to choose? And there's also something called MLPerf that you might have heard of that has this purpose of evaluating hardware accelerators. But it doesn't have that many models, and some of them are getting a bit outdated. So we decided to develop our own model set. And it's a combination of how well known they are and how much state of the art they are. And the parenthesis here would be that it's different configurations of them. So we have currently 9 different models and with 17 different configurations, because ResNet comes in different shape, like ResNet 18, 50, etc. So there's different approaches then to making deep learning efficient, right? So one thing, the obvious optimization, is to, well, most energy and cost efficient way to compute something is to not compute it, right? Or at least compute it with few operations as possible. And as the research community have shown, there's quite some redundancy in these models. They are huge, a lot of parameters, but it turns out that you actually don't need all of them. So there's a lot of different methods since 2015 forward about how to actually do this. And this is one of the main things that we are doing in our company. And then, I mean, it's about the runtime and compilation of that. So when you want to make a computation, you make it as local as possible. The data transfer is the bottlenecks in deep learning execution. So it's very important to use algorithms and that reuses local memory as much as possible, and also in the design of the accelerators. This is very important. And well, once you've done that, I mean, you should run this local computation on efficient hardware. And the most efficient is if you, well, create your own accelerator. And the least would be a general purpose like a CPU. Yes, so this relates to different things that we do in the project. It's optimization engine then that optimizes models, and compilation and runtime. We are not that focused on in the project, but we are focusing on evaluating hardware as well. So in terms of optimizing then, how would that look? A little bit more detail. So you can give the system requirements in for example, latency. And you have your model developed, for example, TensorFlow or another supported framework. And you would run the optimization from Python API, and the system would clean up the graph and optimize it using various combinational methods, and then interface it with interfaces for hardware and compilers. And then you have a model that you can execute on the hardware that you have selected. And as you understand from this, then you can, if you have one model, you can then evaluate it on different kind of hardware. So we spent quite some time in the project looking and procuring and analyzing hardware that's commercially available. And what we did first was sort of a paper study on this to see the spec sheets and made a comparison. So this is the comparison from the spec sheets. So it's quite different devices and IP cores here for execution on an FPGA. And yeah, and these data here, the performance in giga operations is supplied by the actual vendor. So currently we are actually procuring and evaluating them and see if we get to close to these values. And these are the power also provided by the vendor. So another thing that's quite interesting. So what's the next step from this? What did we say here? We said that we have optimization and did that. And then when we're done with that, then we use the compilation and then we run it on some fixed hardware, right? But if you have flexibility in the hardware, well, you can also have them, and we have the flexibility on the model side. So you can also use this flexibility on both the hardware and the software to do what's referred to as co-design. So you design both the software and the hardware together. It's also known as architecture. So which is then a combination of this optimization of deep learning models and computer architecture and the designs of accelerators. So this first case here refers to what I've shown in the previous slides. Well, you have the model, you optimize it, you compile it, and you run it on some available hardware. But with the architecture co-design, well, then it's an interplay between deep learning model optimization or design of the model and this design of the actual hardware. This is very, very interesting and could be potentially very good for efficiency. So with this said, the fun has just started. So you can follow our work on Twitter, on LinkedIn, and the Vedliot website is vedliot.eu. And with that, I say thank you and open up if there's any questions. And thanks for allowing us to come here and present.
Okay, so this was, indeed a different perspective, right? More oriented to machine learning pipelines and embedded devices, and maybe I would say easier understandable. I think we are perfectly on time. I don't know if there are any questions from the chat. If not, I would like to make a short recap by thanking all presenters, and also asking all presenters to share the final version of their slides, because we will be sharing these along with the recordings, right, on the NG-IoT page. And of course, we will providing to your projects to share through your dissemination and communication channels. I also keep Carlos' suggestion about the possibility of forming a short group here, and in the months to come, working on a sort of IoT architectures white paper that we can give to the community so that they can learn, but also engage with our projects at a more technical level. That's all from my side. Unless there are any other questions in the chat, I'd like to thank Hans and to thank everybody again, and see you in the next events. Catherine?